Hi everyone, I am Zeng from University of Maryland, College Park. Here, I'm going to present our paper titled A Review and Collation of Graphical Perception Knowledge for Visualization Recommendation. As we all know, visualizations help us make sense of complex datasets. For example, visualizing the COVID data can help analysts or policymakers to better understand the case rate and death rate based on different ages, races, and locations towards making important decisions. However, visualizing data become more and more complicated. Let's say we need to analyze a movie dataset. We not only need to consider the data size and data types, but also manipulate the data based on analysts' intentions. For example, to analyze the relationship between creative type and release date, we need to calculate the numbers of records. And then we need to pick up the appropriate encoding channels for each selected attribute. Therefore, more and more visualization recommendation systems are proposed to reduce human efforts by partially or fully automating the visualization design process. The systems take datasets as an input and then output visualizations to help users better understand the data they are working on. There are some work like Tableau, Voyager, Foresight, etc. have contributed to this research area. The construction of these visualization recommendation algorithms rely on graphical perception works to compare the effectiveness of one visualization design versus another. For example, Voyager systems use the APT and Show Me papers as guidelines to select the optimal encoding channels and mark types. However, none of the existing systems use more than 3 graphical perception studies as guidelines, leaving many more studies excluded from the design of visualization recommendation systems. We find that it is because the graphical perception findings are usually reported inconsistently. And also, there's no shared data across studies, making it extremely hard to integrate many graphical perception knowledge into visualization recommendation systems. Thus, in this paper, we present a review of existing literature in graphical perception and synthesize findings in a format that can be ingested into visualization recommendation systems to guide the recommendation process. We first would like to discuss our paper review process. To identify the graphical perception knowledge for informing visualization recommendation systems, we reviewed visualization-related literature from the last 10 years. In terms of paper collection, we searched for keywords like encoding, perception, effectiveness in the titles and abstracts. We also refer to existing literature to set some boundaries to the visualization space. Otherwise, the visualization space would be too broad and also impractical for algorithms to eliminate. For example, we exclude 3D and network visualizations and only keep static visualizations in this space. In total, we uncovered 132 candidate papers. We also proposed some design decisions to exclude unrelated papers. For example, we only keep papers that tell us which visualization to pick based on different data and tasks. These filtering steps left 59 papers for our analysis. We then develop a schema to record the existing perceptual result of comparing different visualization designs under various tasks and metrics. Here, we use the SIGCHI 2018 paper as an example to demonstrate our schema. We use 6 components to specify each visualization design discussed in the paper. We use data type, data characteristic, and data transformations to describe the data, and mark type, encoding channel, and scale type to specify the visualization design. Our schema can also capture the perceptual result detailedly. The perceptual results are separate into experimental and theoretical rankings. For each perceptual result, we record metric, task, and a rank list showing how different visualizations rank based on the corresponding task and metric. However, the rank list does not reflect whether there's a significant performance difference between two visualization designs. Thus, we also record a significant list that store pairs of visualizations whose performance are significantly different. We can see from the example here, visualization V1 performed the best in the colorate task, and visualization V1, V2, V3 all perform significantly better than visualization V4 in terms of the accuracy metric. For each significant list, we also record the statistical test result, including the significant method and threshold, as well as the effect size, method, and value. In total, we contribute 59 data files, one for each study, recording how visualizations are compared based on different tasks and metrics. Besides recording graphical perception results with a consistent format, we also synthesize ranking across different visualization designs and summarize recommendation rules which system designer or even visualization designer can use when designing their own system or visualizations. Our rules can inform which encoding to pick. For example, we find that position encodings are usually the top choice for all data types. Color saturation and area encodings also perform well in representing quantitative data. Color hue and shape encoding are effective for visualizing nominal data. And color saturations perform better than color hue for representing ordinal data. Moreover, our rules can also inform which chart type to select. For example, we find that bar charts perform the best for the majority of tasks, including cluster, filter, sort, distribution, find extreme, and aggregation. On the other hand, parallel coordinates also perform well in cluster, retrieve value, find anomalies, and determine range tasks. Since no systematic bias is found with point marks, so scatter plots are also top choices for colorate and find anomalous tasks. We have much more recommendation rules presented in our paper. Feel free to refer to our paper if you are interested in knowing more graphical perception findings. Our paper also provides 3 examples to illustrate how our recommendation rules can be used to improve existing visualization recommendation algorithms. Here, we demonstrate one of the examples. Several studies results inform us how to pick appropriate encoding for different data attributes. One research reorders the shape, color, and size encoding to gain better user performance. Another research says that colors are generally more distinguishable with filled shapes than with unfilled ones. Using these 2 rules, we can improve the visualization design recommended by Voyager, showing on the left, to the right one, where categorical data is visualized by filled shapes with a better color scheme. In summary, we review a broad range of literature focusing on graphical perception. We contribute 59 data files, one for each study, recording how visualizations are compared based on different tasks and metrics. This dataset can be directly ingested by visualization recommendation algorithms. We also summarize concrete recommendation rules for algorithms to generate effective visualization design. Finally, we illustrate how our result can be used to improve existing algorithms. Thank you so much for listening to my presentation. If we want to take a look, the paper and the dataset are available at the link on the screen. Feel free to ask if you have any questions about our work, or you can reach out to me by email. Thank you.